Okay, so this is my first part one, if you like, of my aqueous ion videos, the complexy stuff, as part of the inorganic section of the A-level, full A-level specification. I think I teach this in a bit of a weird way in that I tend to do this sort of general kind of lesson first and then do the actual specific copper, iron and aluminium afterwards. So I'm going to do this in the same way, and this is my sort of introductory video that will cover some of the details, but in more sort of specifically, but then some of it will be quite vague as well. So it's a kind of as I said, an introductory video into the whole aqueous ion stuff, which I think helps. I think it makes it a little bit easier because the rest of it's then just loads of revision and repetition. So I'm going to try and keep these quite short as well, this whole sort of series on aqueous ions. So in general terms, our aqueous ions that we're looking at are, and I'm going to use the term M here, to denote a generic transition metal ion of some sort. So hopefully at this point you're sort of happy with the idea of kind of what transition metals are and the fact that they do form these complexes. And this next part of the specification just sort of takes that concept, I guess, a little bit sort of further. But it's the same concept really behind sort of a lot of it. The shape, for example. So these are octahedral substances, and I've got these hexa-aqua complex ions. In this case, M, as I said, is my transition metal of some sort. I've got two different charges, and that's what you're going to come across. You're going to come across two differently charged ions. In the case of copper, it's going to fall into this category, the H2O6 2+. Iron is going to fall into the category of iron 2 plus and iron 3 plus. It's a bit of a bigger section. And then aluminium is the 3 plus. So there's a good sort of spread between the two of it. And that's all you need to know, aqueous ions. So these are the, as I say, sort of in general terms, with our MH2O6, MH2O6 2 plus and 3 plus. What's really worth kind of making a point of at this time is that, and I don't think people really understand that this is not a full compound as such. This is just a positive ion. So, for example, a full compound made using this one might be something like H2O6 Cl2, and that would be some sort of hydrated metal chloride. And that's its point here, is that this is our negative ion, and this here, the whole thing, is the positive ion. And there's been some questions in the past that have sort of looked at that, and I may cover that in a different video. And it really required that to be understood, that whatever was here was basically the positive ion, and you then joined with the negative ion. So anyway, this is generally what we're going to be talking about throughout the whole thing. Now you need to look at some sort of reactions, and there's loads of equations in this, and there are equations that you just need to learn, there are colours you need to learn. Now I'm not going to do any colours in this first video because M isn't a transition metal, therefore it doesn't have a colour specifically, I can't say that word. But in the next few videos I'll talk about colours and stuff. But general reactions you can sort of look at, and I think it's quite easy, I think, to look at it this way. So we're looking first of all with reactions with the hydroxide ion and with ammonia, and I'll do these. I'll do both of these really. So what we've got is our M H2O6, and I'll do it with the 2 plus. Let's have it reacting with OH minus. And what happens here is that and this is true of every 2 plus ion, when we're just talking about general sort of dilute hydroxide ammonia, not to excess. This is not excess, this is just a little bit going on, just a little bit there. What we'll find is that a reaction will take place and we'll have some hydrolysis going on, and essentially what will happen is the charge here, the 2 plus, tells you how much water is going to be hydrolyzed, not hydrolyzed. That's hydrolyzed, I don't know. You don't actually need that bit there either. Just get rid of that. So what I'm going to have here, I'm going to end up with is, in this case of the 2 plus, and I'll go through this again in a second, you're going to end up with the M H2O4 OH2, and that's going to be a solid. I'll put in some state symbols here as well. Quite a good one, quite one of these topics to really add state symbols in, so just make sure that you're really sort of showing the examiner that you understand what's happening, particularly in these kind of things, because it's about when you have to give observations, you have to give the state as well. So this would be a precipitate. Obviously, it would have some sort of colour to it: blue, green, yellow, aubergine. I don't care really. It's whatever the colour is. To go through again how this works. So what you've got is the 2 plus ion here, that you've got this whole complex. As it reacts to the OH minus, we need to balance this up, so there we go. As it reacts to the OH minus, basically the OH minus ion takes hydrogen from the water molecules that are bound to the central transition metal ion, and it turns two of those water molecules ultimately into hydroxide ions there, and in the process produces two water molecules there. So this is a hydrolysis reaction. The OH bonds within the water molecule are being broken when they react with the hydroxide. But in terms of actually kind of you can work out what this is going to be based on the fact that it's 2+. So because it's 2+, we have reacted with two water molecules and we end up with a neutral complex. Now this neutrally charged complex is solid, and that's true of any of these reactions you come across. If you end up with a neutrally charged complex, it is going to be a solid, and that'll help you massively when it comes to some of the states. Don't say a solution if it's not got a charge. If it's got a charge, it will be a solution. Whether that's true for full life and all the rest of it, I don't know, but it's certainly true of this. So I go down and show you another if I go down and show you another reaction here, the same concept as well, this time with the 3+. Based on my rule before that the 2+ led us to 2 H2Os being used, well the 3+ leads us to 3 H2Os being used. And I'm going to throw in this time ammonia just as a little curveball, and mainly because I'm too lazy to do the whole things again and again. 3+, same process happens. It's the same reaction excluding one of the reactants and the product, but the actual complex and what it becomes is exactly the same whether you use hydroxide or ammonia. So in this case we'd end up with MH2O3 OH3 solid again. Just like the OH minus gained a hydrogen ion, became water, this one also gains a hydrogen ion but becomes a lovely ammonium ion. Should really just make that point about why this isn't charged as well. Each of these, being hydroxide ions, has a charge of -1. So the M here, which is 2+, this is neutrally charged, that would still be 2+. The two minuses here cancel. Here, 3+, 3 minuses cancel. This reaction here you could put into this one here, so you could have the 2+ reacting with NH3, and all it would be is 2NH3 and NH4+. The reason I don't want to keep writing this again and again is firstly it's just time consuming, and it's the same reaction. Provided you can get your head around the fact that the OH minus, the hydroxide ion, becomes water and the ammonia becomes NH4+, with these initial sort of dilute, drop by drop, not excess reactions, then the rest of it's very simple, because these complex to a neutrally charged complex, they remain the same depending on whether it's the 2+ or the 3+, with the reaction of hydroxide or with ammonia. So it's actually quite a simple one to get marks on, because there's loads of learning there, or loads of potential marking points for very little learning. That's essentially kind of that initial part. You can, and I made the point here, this is not excess. You can have various excesses. Words are not working today. You can have various excess reactions going on as well, and it's quite difficult to give you all of those examples. Some of them are very specific to whether it's, I did it that time, that's good. Some of them are very specific to whether it's the copper, the iron, or the aluminium, as to what you will get with the excess, if anything. But in general terms, an excess reaction here you might find, and this is in general terms, I'm not suggesting this always happens, because it doesn't, but you could find something like the 2+ might go, oh by the way this is aqueous here as well, and all the rest, that's an aqueous solution. The 2+, if we react it with excess, just OH minus, what we could find happen, and this may happen, this may not happen, is that we would end up with something like this going on. This would change our charge now down to 4-. Again, balance this up. So the 6 H2Os there, 6 OH minus there, and that's all balanced. Now, the excess reactions, generally speaking, come under the sort of the umbrella term of ligand substitution. Now, of course, at this point, you know what ligands are. They're the things bound to the central metal ions. If you don't know that, you need to seriously go back and have a look at stuff and check out really what's going on. This reaction is very hard to tell really that it's a ligand substitution, because it looks very similar to the previous one in that you go in really from H2O to OH, which could be just the loss of the H, or it could be a direct swap of the H2O for the OH minus, which both end up with the same sort of end goal, but you don't know how you've got it, whether it's ligand substitution or not. A more obvious example would be something like this one. Where is it? Yeah, there we go. Something like this, where it's much, well, I think it's much more clear that what you've got here is a substitution reaction, because what you've clearly done is you've swapped H2O with NH3. We've now got a hexaamine here, 3 plus. Note the charge doesn't change in this instance because these are neutral molecules. They've got no charge to them, as opposed to the hydroxide ions, which 6 of these gives you a 4 minus in total. So this is an example of what could be classed in this first one as ligand substitution. It's definitely ligand substitution in the second one. But in this particular instance, just the key thing to say there is that there was something I was going to say. I've completely forgotten what it was. The key thing there to say is... No, I don't know what it was. But this isn't always necessarily the reaction that takes place in these cases. Sometimes you get partial substitution, so it could be NH3 for H2O2 in the case of one of the copper compounds. So it's about, this is where I think some of the more difficult learning comes in, because there's some funny ones that can go on. Another example of one of these reactions is, and this is something again which crops up particularly within copper, is if you have your 2 plus, one in this case, and we add something like concentrated hydrochloric acid, and you can see most of these reactions happen for yourself. We end up producing this little guy. This is going to be 2 minus, like that. So we produce this thing here, and this becomes this tetrahedral complex here because the chloride ions are too big, they're too fat to have to fit all 6 rounds. We can only get 4. They're tetrahedral. Charge changes because again the chloride ions are negative ions. Within this one, this is one where there's a bit of an example of a particular type of effect that can go on as well. There's a tie over, a bit of sort of overlap really between this section, the thermodynamics, and they are on the same paper, which I think is paper 1. Yeah, paper 1. In the thermodynamics, the idea of entropy and sort of Gibbs energy and all the rest, you've got this thing within, particularly within this aqueous ion stuff called the I call it chelate. It could be chelate. I really don't know. I call it chelate. It looks like that. But this particular effect, where essentially it leads to sort of stability of various compounds. These are bad examples. I'll come on to why in a second, and I'll do this quite quickly. And really, it's just all about sort of thermodynamics. So I'm hoping this isn't where I want to cover thermodynamics, but I'll just apply it to this particular instance. If you look at sort of what's going on here, and this isn't the best example to use. Often within these ligand substitution or hydrolysis reactions, the bonds that are made and broken are very similar, if not the same. Therefore, the overall enthalpy of these reactions tends to be fairly low, if not almost at 0. It's a very, very small enthalpy change. Therefore, the idea of sort of whether the reaction's feasible and stability kind of comes into play, particularly in relation to entropy. So if we looked at this first example here, let's say first would be the first and only example. If we were to pretend that entropy-wise there's nothing going on here, well, from an entropy point of view, we've got 1 molecule, 4 there, so we've got 5 becoming 7. So what we've got is an increase in entropy going from this side to this side, and there are better examples out there, and maybe one of the questions in the next few videos we'll try and squeeze one in that shows you the chelate effect. But 5 to 7 means we've got an increase in entropy, which means this reaction is more likely to happen going from this particular instance through to the other. Therefore, in reverse, it's much less likely to happen again because enthalpy change in this assumption here, this is almost 0. Enthalpy change would be negligible, and therefore going from here back to here, we would probably find that actually very unlikely to happen because we're going from 7 to 5 molecules, which is therefore a decrease in entropy. So it's an interesting sort of application, if you like, of sort of feasibility and Gibbs and all the rest of it, particularly in relation to the fact that normally, and make this really clear, the bonds broken and made are very similar. Therefore, there's almost, for many instances, there's almost 0 enthalpy change, and it's entropy that takes into account, particularly the number of molecules going normally from a lower to a higher number, therefore meaning that the compound that's made, in this case the tetrahedral little guy here, that ends up being more stable. It's more happy in that thermodynamic sort of situation. So that was just a point sort of really I felt thrown in there. And the last bit that I want to cover within this oh no, I've reached the bottom. The last bit that I want to cover, sideways. Oh no, I've reached the upside as well. Oh, it's all going wrong. It's all going wrong. Is this a oh no, I'll have to just do it here, won't I? The last bit that I want to look at is the acidity of the complexes. Acidity of the complexes. So, in this particular instance, don't want to get rid of no, I'm not going to get rid of you. I'm going to keep you. Okay, we've either got the M 2 plus complex or we've got the 3 plus complex, and that's going to cover you for all of your copper, your iron, and your aluminium. And you need to look at how the acidity of those 2 plus and 3 plus complexes change. And so what we find is that if we just stick both of these down for now, it's 206, 3 plus and 2 plus. These have different acidities. They would have different pHs, even if it was the same metal ion based on the 2 plus and the 3 plus. And the reason is that in particularly the 3 plus case, this metal ion there has a higher, no, it's higher, not higher because it's comparative, higher charge size ratio, which ultimately means that this thing here is more polarizing. And how that translates into sort of the reality of the situation is that this metal ion, ultimately, when we have our actual whole complex, like this, and that's just one of my lone pairs. There's two obviously on oxygen, but we can ignore the other one. This is my complex and just one of the ligands drawn of what would be 6. The fact this is 3 plus means that it has an overall bigger effect, being that it's more polarizing because it has this higher charge to size ratio. If we're directly comparing the 2 plus and 3 plus with the same metal ion, same size roughly for each one, this has a higher charge though, therefore a greater charge size ratio. So what this does is it has an effect within the ligand that's bound. In this case it's going to have an effect on this hydrogen, and what it does is it essentially pulls all these electrons towards it, and that's this sort of polarizing effect. It's dragging electrons towards it, and the end result is it actually weakens this bond in the case of the 3 plus. And because this bond is weaker, it's more easy to lose that as an H plus ion. And obviously the more easy it is to lose a hydrogen ion, the more acidic that thing would be. It's more easy to lose it, therefore it's acting as a better acid. So the 3 plus ions are always acting as better acids than the 2 plus ions because of the higher charge size ratio of the transition metal ion, which gives it a more polarizing ability because the hydrogen ion is more easily lost. And if we look at how this affects the reactions, there's a particular type of reaction in that this accounts for, and that's the reaction of these metal ions, these complexes, with carbonate ions, and they're going to react in two very, very specific ways. The reactions, I'll put some state symbols for this one as well. You've got what I think is a more sort of classic carbonate and acid type reaction at the bottom here. Top one's a really easy one though, because the top reaction is literally just this MCO3, and we're going to produce 6H2O. State symbols there. This is going to be a solid because, as I said earlier on, this is our sort of mini complex if you like now. It has no charge, therefore it is solid. Down here, this one's a little bit more of a hassle of a reaction. It does not produce this guy here. Instead, what we produce is that same, it will be neutrally charged, but that same complex as to when we added the ammonia or the hydroxide ions in sort of drop by drop, not in excess. And that's that sort of H2O3 OH3 solid. But then it also has, annoyingly, because our charges need to balance here, we've got to do a bit of tomfoolery. We've actually got to balance it like this. And then finally we stick in 3 CO2 and 3 H2O. So what we find here is charges are balanced. Oh, now charges are balanced. 6 plus oh, and I looked at that and thought that was something going wrong there. I don't know what I did that for. 0 on that side, 6 plus, 6 minus, cancel, 0 on this side. When you actually look at this, the fact that it produces the carbon dioxide, some sort of, what I'll pretend is some sort of salty type thing there, and the water, that to me is more like your classic carbonate and acid reaction, whereas this one is just a direct sort of substitution reaction going on where the carbonate ion is being switched with the 6 water molecules. That is essentially everything that you need to know for... Oh no, I've killed it. That is essentially everything that you need to know within reason for these aqueous ion stuff. So I'm going to do more videos now that will look at copper, look at aluminium and iron in more detail, but these are general reactions which you'll come back to. So if you can get your head around these now, you'll be sorted in the long run. No questions, because there are no questions generally, but look out for the copper, the iron and the aluminium videos.